Welcome back for the second part to lesson 4.6. We're looking at example 3 and 4. So we're doing some modeling with different exponential and logarithmic, and I'm going to introduce to you a logistic function here in a moment. But example 3 says the population of Florida grew from 17.8 million in 2005 to 19.3 million in 2012. Find a function of the form. The population of T is given of C times e to the kt. So we've got the growth factor, e to the k is like your growth factor, and then C is your starting value or your y-intercept that models the population growth. Here, T is the number of years since 2005. So that's our base year. Okay, there are two ways we can do this. So I'm going to start with what we've kind of been looking at. So we know that the current population is 19.3, and we started at 17.8, and time has been 7 years because 2012 minus 2005 is 7, since 2005 is our base year, so T is 7. So if I divide by 17.8 and take the natural log, that gets rid of k or e, and we have 7 times k, and then we're going to divide by 7 to find k. And so our model is going to be P of T equals 17.8, because that's our starting value, times E, and then we're going to raise that. And then when we put this in Desmos, we can find out what K equals. So I'm going to show you that here in Desmos. So right here is that calculation in Desmos. So K is 0.01156. I'm going out 5 decimal places just because it's such a small number, times T is our model. I also wanted to show you how you can do modeling in Desmos. This class is not really a modeling based class. I wish it was because I think it's very valuable. But so if we were to put our 2 data points in X1 and Y1, you can create this table by clicking the plus sign and saying I want to make a table, and you can make a new one. But we're just going to use the one that I have here. And then I'm going to say I want to model Y1. I want to predict Y1 with this tilde symbol and using this model. So this is our exponential model that we've been working with. And I can tell it I wanted to find the parameters K and C given the data in X1. And we can see the graph here. I'm going to hit this magnifying glass right here where my mouse is on the left. See where my mouse is, the magnifying glass, and it's going to show me the graph. So this is the exponential model. I'm just going to zoom out so we can see it. So that's the exponential model that it's predicting. And oddly enough, it does predict that our starting value is 17.8. That's what they told us. And it predicts my K is going to be exactly what we found as well. So 0.01156. Then, so there's our model. It says use your model to predict the population of Florida in 2015. So we're going to find P of, so 2015 is actually 10 years, or T equals 10 after 2005. And so I'm going to put that in. I'm going to show you in Desmos here. So I could put it into the equation, or I can just grab this model that we created, which is what we want to use. And I want to find 10. And it looks like these are going by 20, 40, 60, 80. So these are, so 10 is right here. It's actually, there it is. So it's about 19.98 million. Almost 20 million in 2015 is the predicted amount. Part C says, I want you to look up in the internet the population of Florida in 2015. Florida population population. So, U.S. Census Bureau. I don't know if we can quickly find 2015 or not. I think we can go to the Worldometer site and look at population. They've got a lot of data there. We can go to the United States. And then I think we can even search. Um, let's see. We should be able to find. The Gotta get some kind of estimate here. Here we go. So 2015, 2000, okay, there it is. 2015. So the actual population was 20.2. So 20,219,111 was what they're estimating here on this website. So we underestimated a little bit. And that's okay. But it's always good to see what how your model is actually estimating here. A lot of people moved to Florida after COVID, so that might, but that was before COVID. So yeah, we were pretty close, but not quite there. Okay. The last model I want to have you look at is called a logistics model, and it's used in medical. It's also used in animal and wildlife, like preservation of populations of animals. It's a logistic function, and its parameters are C and A and B. You can see B is right here. So it's C over 1 plus A times e to the negative bx. So A, B, and C. So you can see the function climbs very quickly and then planes off. And this is how a lot of viruses work. So when a person, when a virus happens in a community of people, it spreads really quickly and it looks like it's exponential, but then it tapers off at some point. And so that's why we use this model to model those sorts of situations. So it says the spread of the flu in an elementary school can be modeled by a logistic function. The number of children infected with the flu virus T days after the first infection is given by this function. How many children were initially affected with the flu? So that would be at T equals 0. So that means N of 0 would be 150 over 1 plus 4e to the negative 5 times 0. That means we're gonna have 150 over 1 plus. This is gonna become 0. Negative 0.5 times 0 will be 0. E to the 0 will be 1. And so 4 times 1 is 4. So that's 5. So 150 divided by 5 is approximately 30 students had the flu at the beginning. Then it says how many children were infected with the flu virus after 5 days. So then we're going to put in 5. Now we also want to know after 10 days. So let's go and put the function into Desmos. Here we go. And negative 0.5. There we go. Other one here and turn off the other data. And just say y equals that. Okay. And let's see if it'll let me make a table here. Okay. And so if I make a table on the bottom of the table, I can hit the magnifying glass so it will adjust. There we go. So now we can actually zoom out just a little bit and see the picture, the whole picture. So there's my start here at 30, and then it's climbing fairly quickly, and then it planes off. Looks like there is a asymptote here at about 150. And that would make sense because our number could never get bigger than 150, which is what our numerator is. So if we wanted to put in the table, we wanted to say after 5 days and after 10 days. So I can put that in our table. So after 5 days, it looks like N of 5 would be about 113, 112, or 113 students have the flu. Children. And N of 10 is approximately 146 children have the flu. And then it looks like it maxes out at about 150 students. 20, 40, yeah, about 150 students, and no more than that get sick. So that is a logistic function for you. And that wraps up lesson 4.6. So you can start on the review and catch me back for new videos for chapter 5.